So let me introduce Neeraj, who is our second speaker. Neeraj is a colleague at Nutanix, who I have tremendous respect for. We go back a few years. We've been working together on a few things. And on the side, I don't know how he's able to manage time to go through all the Postgres code and get back with such beautiful slides. His slides are always full of pictures. So on his work, he's got this deep expertise in database internals and large-scale systems. And today he'll be talking about concurrency control and MVCC internals. I've skimmed through his slides, a lot of depth. The first one was on the breadth level. You could see a lot of things. Here, you will see the same boring old thing. How does it work internally, right? So let's look at MVCC snapshot isolation. How do snapshots happen? How does Postgres make sure without explicit locking to serve things concurrently? So over to you, Neeraj. I think the less I speak about it, the more safe I am. You are the expert on this. So yeah, please go ahead.
Okay. Thanks you for the intro. Okay. So at a very high level, we'll start with the notion and semantics of concurrency, how Postgres implements concurrency, what are the building blocks of the concurrency, that which is MVCC, and then we'll talk about how these building blocks interacts with the other parts of the Postgres, and how is it used. Okay, so when we talk about concurrency in database, what it essentially means is that, let's say you have a couple of clients, they should be able to access the same rows at the same time. For example, one is reading, that should be allowed. Another one is writing the exact same rows, that should be allowed. Now, there are a couple of ways to implement this, without, having race conditions. That is, either you acquire a reader's lock or a writer's lock. But in that case, if someone is holding a writer's lock, then the readers will be blocked and vice versa. Okay. But Postgres actually does concurrency very differently. And see, one thing to note about here is that concurrency essentially doesn't mean parallelism. So what it means is that two clients, they cannot update the exact same row at the exact same point in time. Okay, one of them will have to wait, and depending upon the isolation level, one of them will get kicked out. Okay. So the implementation of Postgres for concurrency is called the multi-version concurrency control. So essentially what it means is that all the transactions in the system, they see a snapshot of the database at a given point in time. Okay. Now, in order to implement this, there are a couple of things implemented at the IO layer, and how the transactions are handled. Okay. Couple of pros and cons over here. That the pro is that there are no locks, there are no read locks, there are no write locks, and then since there are no locks, there is no question of deadlocks, and more or less it actually offers much better performance than with readers and writers locks. Okay, the downside of this is that there is some amount of write amplification which is involved over here. We'll see what exactly is that. Okay, and okay. And before we proceed, so Postgres offers 3 levels of isolation, which kind of does a trade-off between performance and kind of a consistent behavior anyone would expect. Okay, so we'll look at them. Okay, so before we go ahead, this is what a multi-statement transaction looks like. Okay, so the first instruction over here, Postgres calls it the top level transaction. Okay, and everything, all these statements inside it, they are the sub transactions. Okay, so yeah. Okay, now from the building blocks perspective, at a very high level, the entire story of MVCC, it relies on 2 things. One is the snapshot, and second is the immutability of the heap tuple. Okay, so row is called as a heap tuple in Postgres. That's what the technical name is. Okay, so what exactly a snapshot is? So when a transaction enters the system, Postgres gives it a view of the system. That what it means is that These are the transactions which are committed before you begin. These are the transactions which are in progress when you came into the system. Okay, very simple notion, very simple idea, but very effective. And to create a snapshot, it's basically just a couple of function calls. There is no, in Happy Path, there is not much IO involved over here. So, creating a snapshot is essentially a very lightweight thing. Okay. And so, since now let's talk about the multi-version part in the concurrency control. So Postgres, whenever a data is persisted onto the disk, it is essentially immutable. Any transaction which updates the data, Postgres creates another version of that data. So that is basically the tuple. So Postgres creates another version of that tuple. It does some bookkeeping as to which was the transaction which created this row and things like that. Okay. Now, say for example, there are a couple of insert and update statements which in succession created new version of the tuple. Some of them were committed successfully. Some of them were rolled back because of one or the other things. Okay, so those transactions which were rolled back, their tuples, it will still exist on the disk. Okay, and essentially what they are called is that tuple. Okay, so that tuple, they keep on getting accumulated over the period of time, and then there's a process called as vacuum, which kicks in periodically, or it's like basically user configurable. Vacuum will kick in. It will kind of remove the dead tuples, make all the data contiguous, and things like that. Okay, so that's why in the MVCC implementation of Postgres, there is some amount of write amplification, but it's actually basically worth it because the reads, they get better performance because of this. Okay, so now we'll look at a couple of the data structures which are used over here. So essentially, snapshot, it's represented by snapshot data struct inside the Postgres. Okay, I have just presented a couple of key fields over here. There are actually many fields. And if you look at the source code of Postgres, all of them have been documented very beautifully. So, just you look at it, you understand what they do. Okay. But in bare minimum, my snapshot contains a couple of things. What is basic xmin, xmax transaction pointer, sub-transaction, and the snapshot time. Okay. So we'll look at them. So xmin is basically when a transaction entered into the system, what all transactions have been known to be committed. And that should be visible to the transaction which is going to execute. Okay, xmax is basically my boundary that all the transactions after xmax, I know that they have been in progress when I came into the system. They have been committed. They might not have been committed. We don't really care about them. Okay, and xip is all the transaction which falls between xmin and xmax. They could be in progress. They could be completed by the time we reach certain statements. Okay, and sub transaction is so. If you see these statements, so these inserts and if there are a couple of more inserts, all of them, they'll be captured into this sub transaction array. So essentially, you have a top level transaction, and if the transaction has more statements, and all of them will be captured into the sub transaction. Okay. Now, Postgres actually supports couple of type of snapshots because snapshot has a very intimate interaction with the isolation levels. So few of them are that one of the type of the snapshot is the MVCC snapshot, which is essentially what we are referring to over here. Another one key type is the self snapshot. So basically all the changes which my transaction has been doing, okay, that has to be visible to me. It is visible to any other transaction or no, it doesn't matter. Okay, so basically MVCC self, and if you were, for example, there is a master and slave kind of a thing going on, then even there will be a snapshot going on at the slave side as well. Sorry, the replica side as well. Or if you are performing a backup or recovery, then there will be a snapshot there as well. But that's fine. We won't be discussing much about them. Okay. Any questions so far on any of the things? Okay, all right, we can proceed. Okay. Secondly, this is what your heap tuple basically looks like within the source code. Okay, there are again several fields in the source code, but we'll talk about the key of them. Okay, so all the heap tuple, they have which transaction created them. That is basically my txmin, and all the heap tuples, they have txmax, which is essentially which transaction deleted them. Okay, and then there's also a info mask bit flag, which captures various states of the tuple as a transaction proceeds. So for example, is this transaction committed, or uh, is this heap tuple, was it moved in the disk by the vacuum process or not? Okay, yeah. So essentially, any tuple which has a non-zero txmax, it's not visible. What it means is it has been deleted. If xmin and xmax both are equal, the meaning is the transaction aborted. Same transaction which inserted it, it was aborted, and that's why the tuple never made it to the system. As a side note, xmin and xmax are actually the columns which are available to all the Postgres rows. So, if you fire in select query, if you say xmin comma xmax, you will be able to see the xmin and xmax. Okay. So logically, this is what a snapshot looks like. Okay. So this, the dotted line over here, that is my transaction timeline. Okay. So all the transactions in Postgres, they start from 3. 3 is the first valid transaction ID which could be assigned, and it goes all the way to 2 raised to 32 minus 1, because the type of transaction is unsigned integer. Okay. So xmin, xpax, and subtransaction ID. And say, for example, this is my transaction which is executing, which is at this particular point. Okay. So everything to the left of my snapshot, all the transactions are definitely committed, and when my transaction should really see the effect of them. Everything which is on the right hand side of the xmax, they could be committed by the time we finish the execution, or we are in the middle of execution, but it really doesn't matter to them. Okay. And again, the xip and sub transaction ID are the list of transactions which have been created by this transaction, or something which exists between both of them. Okay. Now, very briefly, we will see that how snapshots are taken for the isolation levels. Okay. So Postgres provides 3 isolation level: read committed, repeatable read, and the strictest and then the greatest of them all, snapshot isolation. Okay. So in repeated read committed level, each and every, so in this setup, I have my a top level transaction ID 3019, and then there is another transaction 3020 which is executing in parallel. Okay. So the way in which the read committed works, each and every statement get its own snapshot. So when I execute a select, it will get its own snapshot. When I execute a second snapshot, it will get a fresh snapshot of its own. Same thing about the update as well. Okay. But all of these snapshots, they only contain the data which has been truly committed. No dirty reads are allowed in Postgres. There are actually some databases which do allow dirty reads. Microsoft SQL is being one of them, but Postgres doesn't allow the dirty reads. Okay. Now, this transaction level, it is susceptible to something called as some anomalies. Okay. So 2 anomalies: phantom reads and read skews. Okay. And it happens because of these particular thing, that since each transaction get its own snapshot, between 2 transactions, it is possible that something has been updated. So both of these select statements, they will see a different amount of data, even though they are part of the same transaction. Okay. So it is possible that my successive selects, or my where clause, it will see a different type of data than what it was at the start of the transaction. Okay. The second isolation level is the repeatable read isolation level, which basically takes care about the phantom reads and the read skew anomaly. So when this works is, I get one snapshot at the start of the transaction. Okay. All my subsequent statements, they don't get a fresh snapshot. They work on the exact same snapshot. Any changes, they happen in between, it's not visible to me. So my successive selects, my where clause, and my update statement, they see the exact same amount of data. Okay. But now here's the thing, that while I'm performing the update, assume that this transaction hasn't finished yet. Okay. But it was more senior, in a way that it came to the system. So Postgres will actually wait, till this update statement is finished. then it will proceed to kind of execute this update statement. It will reevaluate this where clause, and if nothing has changed between this and this, it will execute this statement. If it has, then repeated read isolation will kill the transaction and throw back error to the user. Okay. Now let's talk very briefly about the snapshot isolation. So from the snapshot perspective, it works exactly in this way. Okay, but it gives you more stricter guarantee that there are, let's say, n number of transactions in the system, and the end state of my system will be such that all the transactions have executed one after the other in a serial order. Okay, so in this case, serial isolation, it will find that there was some read and write dependency between them, and it will actually kill this transaction, and it will ask to ask user to redo the transaction. So there has to be absolutely no dependency between two transactions at all. Okay. Any questions so far before we proceed? Okay. Yeah. Can someone give mic to this gentleman?
You mentioned tuples. So what were those tuples? How are they defined?
So tuple is essentially your data on disk. What you say row, Postgres says as tuple.
What I say is what? Sorry.
So what we say as row, as an application developer, internally Postgres refers to it as a tuple. Okay, and since it resides into disk, it's called heap tuple. That's all. Okay.
Sorry, quick question on the previous the slide of the transaction. So how does it decide which transaction to reject? Like whether it is 3019 or 3020? Like
yes.
if there is a conflict.
There is actually a bit of a complex logic over there, but the one which has finished, it has finished. Okay, the one which is in progress, it has to be consistent. So that is basically, something at a 50,000 feet level. But things what happens internally, it's actually quite intricate and very interesting.
Okay.
Any more questions?
Can you please go to the previous slide? So for 3019, that transaction, what could be the effect if instead of select, it was update statement?
Say that again.
First one.
Yes.
3019, the first statement is a select statement. What would be effect if it was a DML statement?
Same thing.
Same thing.
Yeah. So even if it is DML or a query statement, everyone gets its own snapshot. But then, say for example, if this was an update statement, okay, then Postgres' conflict resolution will kick in, and if say for example, let's say if someone has deleted that row, then there will be no effect of that update. Okay, but if someone has changed that update, that update is no longer valid, then that would be rejected.
Okay. Yeah, thanks.
So that's why you have things like insert on, update on conflict and those kind of a statement. So when you go to for insertion, the tuple might have been created. So instead of insertion, do an update.
Hello.
Yeah.
So somewhere you mentioned, like if you go back in few slides, you mentioned that you are storing max of, no, not this one. You're storing max of concurrent transactions, like max ID of them. So where is it getting used? Is it getting used in any of the isolation level? Can you explain that?
Yes. So say for example, I'm executing an update clause. Which rows should be visible to me? Okay, the one which has been committed, or the one which has been committed by any of my sub transactions. Okay, so that's where the Xmax is used. So if something has not been created by me, but if it falls outside of that Xmax, I don't need to see the effect of it. Okay, I'll actually cover that. That's actually a detailed algorithm for that.
Sorry, small follow-up. So even for read committed isolation level, you're saying
Yes.
we will take till Xmax, like
Yes.
that was defined in the beginning, right?
Yes. So when I say about this Xmin Xmax, it's applicable everywhere. It's applicable everywhere. Okay.
Initially before Postgres version 9.1, the snapshot isolation was not strictly serializable.
Can you repeat? I can't hear.
For Postgres version 9.1, the snapshot isolation level at serializable isolation level was not strictly snapshot isolation. It used to give write skew problem as well. So in the next slide, where you said that here write dependency will be detected and it will not update it, and we will have to retry the transaction. So is it snapshot isolation or serializable snapshot isolation that you are talking about?
It is SSI, serializable snapshot isolation. Yeah. So, by the way, a great thing about the serializable snapshot isolation is it was implemented by the legal department of Wisconsin courts. So just think about it. There was a court department somewhere. They had a problem and they went ahead and implemented the serializable snapshot isolation. So that's, the power of the Postgres community is. Okay, so going ahead. So this actually, this view, it makes sense logically, but physically there is a discrepancy over here. Recall that Postgres is a multi-process system. Every transaction or basically every client connection is a process in itself, okay? So in order to create this snapshot, Postgres has to actually look at each and every process which is running in the system, okay? Now, if you have done any kind of, systems programming or programming in general, if something is accessed by multi-process, it has to be in the shared memory. As soon as it's in the shared memory, it has to be guarded by locks and whatnot. Okay, and as soon as we talk about locks, and if it's in the hot path, there's going to be a performance degradation. Okay, but Postgres actually handles this thing very seamlessly. Okay, let's just see how. Okay, so my snapshot information, it's derived from couple of structures within the Postgres. Okay, so first and foremost of them is the pgproc struct. Okay, each and every Postgres backend, it has a pgproc struct, and what this pgproc struct captures is that so far, what is the minimum transaction ID which I have seen in the system? Okay, so essentially the last known committed transaction which I know. Okay, if this particular backend, as it is said in the Postgres, if it is executing any transaction at present, then what is its transaction ID? Okay. If that transaction has any sub-transactions, then what are the sub-transaction ID? And finally, what's as a backend process, what's my process ID? Okay. So a couple of these fields. So these fields, they are reflected into another structure called proc global, which essentially in turn is a shared memory struct. Okay. So pgproc, all the structures, they do have it, but it's not shared. Proc global is what is exactly shared. Okay, so this proc global, it has a complete copy of the pgproc, and just for the faster access, it has all the transaction IDs which is being executed in the system at any given point in time, or it's listed as a very sorted array. Okay. After this, you have one more structure which comes into picture. So trans-aim variable data. Okay, so basically it does two things. What is the next transaction ID I should assign to any of the backend process? Okay, and what is the last known maximum transaction ID which I know has completed? Okay, so in effect, any transaction which starts in Postgres, it refers to this next XID. Okay, it acquires a very lightweight log, takes that next XID, increments it, and gets its work done. Okay, last completed transaction ID just needs same way it needs the reads and write logs, read it, and just be done with it. Okay, so say for example, I know what the last completed transaction ID is. If I just increment it, I know what the Xmax is. Anything which is equal to Xmax or greater than that, my snapshot doesn't care whether it is visible or not. Okay, so you take all of these three structures, apply some good aggregation logic, and finally what you get is a snapshot. Okay, yeah. So now we'll just see that how, snapshots come into the picture and how exactly Postgres considers the snapshot and determines whether a row should be visible to a transaction or not. Okay. So everything at a very high level starts from these 4 or 5 functions in happy path. Heap begin scan, heap insert, heap update, or heap delete. Okay. So just to reiterate, anything which resides on the disk, Postgres calls it as a heap. Okay. You need to manipulate or access that heap. You need to use any of these well-defined transaction. Okay. So at some point down the line, these functions, they will take the snapshot data, which is essentially constructing this. Then there's this function, couple of functions basically, which gets called with the heap, basically the tuples or the rows, which were part of the select query. Okay, I have some rows with me. Now I'll, apply some logic and see that according to my snapshot, which of these rows should be visible to me. Okay, so it's taken care by couple of functions. The one which we'll be discussing is heap tuple satisfies MVCC. Okay, so same way as MVCC itself, there's another function which basically my vacuum process uses to know that which tuples should be vacuumed off, or which tuples it has deleted. Okay, so at a high level, this is what how you take a snapshot of the data. Okay, first of all, you have a look at that trans aim variable struct. Take the last known completed transaction ID and increment it by 1. Okay, you'll get the Xmax, plain and simple. Okay, then assume that my Xmin is my Xmax. Okay, now next step, go to this my pgproc struct, that is the backend's pgproc struct, and take my transaction ID and check that am I the transaction min by any chance. If it is, then Xmin becomes the XID, and we proceed further. If not, it directly goes to it directly goes to this particular field. Yeah, the XIP, which is basically the in progress transactions. Okay, then we iterate over each and every running transaction ID on the system, and we check that is any one of them the minimum transaction. If it is, great. If it is not, then if it is not, then put it in the XIP, which is again the transactions which are running. Okay, post that, go to that. Yeah, I mean the process is just pretty much just like this. So we calculate Xmin, we take account of each and every top running transaction ID, and we populate the XIP. Then we go to each and every backend process and see that what are the sub transactions which they are running, and just simply just append it over here. Okay, since my transaction ID is an monotonically increasing number, if I have to find any of the transaction ID in any of these fields, it's a matter of a simple binary search. Basically, if you see the code of Postgres, how do you know whether a transaction is in this? It's essentially binary search, nothing else. Yeah. So okay, so that's how you actually create a transaction snapshot, looking at a couple of structs. Okay. The actual implementation is actually it's very intricate. We acquire readers lock at a couple of places, and other than that, we also take into account some of the information which is required by the vacuum process. But just for the brevity's sake, I've just skimmed it over. Okay. So once we have the snapshot with us, okay, now how do we decide that? So this is what the function signature is. I have a row, I have a snapshot. Now, according to this snapshot, is this tuple, should this be visible to me or not? Okay. So this particular function, it does the reconciliation between what is present in the disk and what my snapshot is saying. Okay. So in order to do the reconciliation, it consults this particular field, the t-info mask. Okay. So essentially what it does is it reads the t-info mask. If t-info mask says that this transaction has been committed, okay, it has an xmin which has been committed. It has an xid which is not committed. So this row, it's not deleted. Okay. So this row, it is in existence. Great. Did the transaction which created this particular heap tuple, is it outside of my xmin? If it is, then this should be visible to me. If it is greater than X max, then we don't care about it, and it shouldn't be visible. Okay. If it is somewhere in between, then what I need to check is that did any of my transaction created this particular tuple? If it is, then I have to take care into account that whether if it was an update statement, then it should be visible. If the row has been deleted, then it shouldn't be deleted to me. Okay. Another bit of a complexity over here is that was this tuple moved to a different location by the vacuum process? And am I the vacuum process, which is doing this transaction? If I am, then the effect of this movement, it should be visible to me. If I am not that vacuum process, then again, I'll check the bounds. Is the transaction ID, outside of the X-bin horizon, then it should be visible to me. If it is not, if it's above X max, then we really don't care about the. Okay. Yeah. So this is pretty much it. You construct a snapshot, you apply it to each and every tuple, you use some logic, and that's how you get really nice and simple MVCC in Postgres. Yeah. Any questions now?
Out of the two isolations that we discussed, right, which one has a better performance and like
Read committed. So even the official statement from Postgres is that read commit gives you better performance, and it solves your 70 to 80% use cases. But if you more stricter guarantees, basically, if you don't want the read skews or phantom reads, go with the read isolation. And if you know that you have a very contentious system, you want a very strict ordering, go with a snapshot isolation. So snapshot isolation, it is lightweight, but it doesn't perform as well as read committed or repeatable read.
so by default it is read commit, right?
It is read committed. You have to explicitly mention that what other thing you want. If you don't mention, it's read committed.
Okay. Yeah. Thanks.
More questions? Any other questions? Okay, yeah. Thank you, Neeraj. Very insightful. I'm sure I'm going to watch the recording and make some bookmarks and sort of dig further. And if you have more questions, you know who to reach. Yeah. We have a vote of thanks for Neeraj, who's done a lot of hard work, digging into code, figuring things out, and trying for himself. So yeah, please give a big round of hand for Neeraj.